Okay, here we have lesson 9. So we're going to investigate multiplicity a little bit more. So it's actually a little bit more complicated than the last lesson made it seem. So if we were to now graph these three graphs, x minus 2 cubed has a y-intercept of -8. So it's here, comes through, and it has a 0 at 2. It's probably not quite as horizontal there as I've drawn it, but next one, graph of 2, x minus 2 to the 5, has a y-intercept of -32. So that's about here. And comes here and comes up. So that's the one with a power of 5 and a power of 7. Has a y-intercept of -128, so that's not even going to fit on our graph. But it also has a 0 here, changes concavity, keeps going up. So what happens? Well, there's a point of inflection for all the graphs at that x-intercept. So just because there's a point of inflection in the last lesson, we said, oh, that means it's multiplicity 3. It actually means it's any odd multiplicity other than 1. So, and the same thing goes for evens. We would find that x minus 2 squared looks like this. The next one, x minus 2 to the 4, is a little bit steeper. And then the next one is steeper still. Looks like that. So here all the graphs are tangent at the point 2, 0. So if we see that the graph is tangent at a certain 0, that tells me it is multiplicity 2, 4, 6, 8, or anything even. So real 0 of even multiplicity, 2, 4, 6, or 8, etc., occurs where the graph of a polynomial function is tangent to the x-axis. A real 0 of odd multiplicity greater than 1, so 3, 5, 7, etc., occurs where the graph of the polynomial function has a point of inflection on the x-axis. The sum of the multiplicities of the zeros of a polynomial function is equal to the degree. So here we have 4 graphs that we're going to use for example 1. Example 1 says, in each case, state the number of distinct zeros and possible multiplicities. So I'm going to label this on the graph itself here. So here we have 2 distinct zeros because it has 2 x-intercepts. And possible multiplicities, well, this one is tangent, so this must be an even multiplicity. This is a point of inflection, so this must be odd, but bigger than 1. The second one here, this one now has 3 distinct zeros. This one here must be multiplicity equal to 1. I'm just going to use an M there because it passes straight through. So if the graph passes straight through the x-axis, we know it's multiplicity 1. We have no other options. It's tangent here, so this must be even multiplicity. Graph 3. Again, here we have 1, 2, 3 distinct zeros. These 2 are tangent, so they must be of even multiplicity. This one passes straight through, so this is multiplicity 1. Here we now have, again, 3 distinct zeros. This passes straight through, so multiplicity 1. This one passes straight through, so multiplicity 1. This one has a point of inflection, so this is odd multiplicity, but it has to be greater than 1. So notice it doesn't matter what the graph is doing anywhere else. Like just because it looks like the same shape as a parabola at a certain point doesn't mean we have another factor or another multiplicity. It's only what happens at the x-axis. B, which graph could represent a polynomial function of degree 8? So now you have to start choosing some numbers to see which one could make degree 8. Well, here if we have an even plus an odd, we're never going to get an even number. So it can't be 1, can't be 3, because again I have 2 evens plus an odd will give me an odd number. Same thing with 4. I have an odd number plus 1 plus 1, while an odd number plus 2 gives me an even number, an odd number. So my only choice here is 2. So is it possible to get graph 2 to have degree 8? Well, we know that each of these has degree 1, so that's a total degree of 2 right now. If this was degree 6, we would have a function with degree 8. In which of the graphs is the leading coefficient positive? So remember, for the leading coefficient to be positive, the right arm needs to be going up, so that would be 3 or 4. Both have their right arms going up. Without using a graphing calculator, make a rough sketch of this graph. So we're going to start by labeling our zeros. So we know we have a 0 at 0 from the factor x, a 0 at 1 from the factor x minus 1, and a 0 at 4, probably not a great scale, but 0 at 4 from the factor x minus 4. Well, we know that this is degree 4 plus 1 plus 1. So this is degree 6. So that means both arms supposed to be going in the same direction. The leading coefficient is negative, so that means both arms need to be coming down. So we know that we're going to pass straight through 0. We have even degree at 1, so it touches, comes back up, and then passes straight through 4. Now we really don't know how high those peaks go or which one is higher. All we know is what it does at the axis. So to get a more accurate diagram, you would now need to go to your graphing calculator. The following graphs represent polynomial functions of lowest possible degree. State the degree of the polynomial function. They often put this in there so that we can rule out certain cases. So now, whenever we see something that's tangent, we're going to say it's degree 2 or multiplicity 2. Whenever we see something that has a point of inflection, we're now going to say multiplicity 3. That's how they kind of steer us in the right direction. Otherwise, there'd be numerous right answers that we could come up with for each graph. So state the degree of each polynomial function. And part B, for p of x, state the points on the graph which represent real and equal roots. So the degree, well, this would have multiplicity 2, that's 0. This 0 would have multiplicity 1. This 0 passes straight through, so multiplicity 1. So the total degree here would be 4. Second part, for p of x equals 0, state the points on the graph which represent real and equal roots. So real and equal roots would be represented by A. D and F would be real distinct roots. B. So now we have a different graph. Now we have points of inflection here and here. Well, since we're working with lowest possible degree, that means each of these has multiplicity 3. And those are the only x-intercepts. So that means this has degree 6 overall. And real equal roots, well, in this case, both of those points are representing real equal roots. Example 4. On the grid, sketch a graph with a polynomial function satisfying the given conditions. Positive leading coefficient, so we know somehow this right arm is going to go up. 1 real 0 of multiplicity 1. 2 real zeros of multiplicity 2. 1 real 0 of multiplicity 5. So this has 2, 3, 4 zeros all together. And you can really draw these wherever you like. The sum of the multiplicities is 1 plus 2, so that's 3 plus 5 is 8. So it's even. So that tells us that both of these arms need to move up. we need to have 2 real zeros of multiplicity 2 and 1 real zero of multiplicity 5. So I'm going to pass straight through the first one. That's going to be my 1 real zero of multiplicity 1. I'm going to be tangent here. That's 1 0 of multiplicity 2. Tangent here again. That's another 0 of multiplicity 2. And then a point of inflection to get me to the final one. There's different ways you could draw it. You can be tangent at different points. This is just one example. Second one, negative leading coefficient. So that means its right arm is going to be going down. 2 real zeros of multiplicity 1, 1 real zero of multiplicity 3, 1 real zero of multiplicity 4. So here I have 4 real zeros. So I can mark 4 x-intercepts anywhere on there. My total multiplicity, I have 1 plus 3. Oh, sorry, I have 2 real zeros of multiplicity 1. So that counts for 2. Plus 1 real zero of multiplicity 3. So now I'm at 5. Plus 1 real zero of multiplicity 4. So that gives me a degree of 9. So I know that my arms have to go in opposite directions. So 2 real zeros of multiplicity 1, I'll get those out of the way first. So I pass through. 1 real zero of multiplicity 3, and 1 real zero of multiplicity 4. So I'm going to go up. I have my point of inflection. Now multiplicity 4, I'm going to be tangent. So state the degree. And I think I made a mistake with this the first time. It is even though. But 1 real zero of multiplicity 1, so that's 1. 2 real zeros of multiplicity 2, so I need to count that 2 twice. Plus 5 gives me a total degree of 10 for the first one. For the second one, 2 real zeros of multiplicity 1, 1 real zero of multiplicity 4, and 1 of multiplicity 3, which gives me a total degree of 9. So this next part's an extension. I can do the whole thing. I just want to look at example 5. So there is such a thing as having non-real zeros. So just because we have a function that has a degree of 5 doesn't mean we have 5 factors. It's possible that some things can't be factored, in which case you see things like this. So the graph is very similar to what we would usually see a cubic function looks like, except this only has one x-intercept of multiplicity 1. So what's really happening here is there are some non-real zeros. So not all graphs, not all factors, or not all polynomials of degree 5 will have 5 factors, because there's parts that will have non-real zeros. So same thing here. This looks like maybe it's a quartic function, but I'm only counting for multiplicity of 2 with the factors I know. So somewhere in here, non-real zeros are happening. So just be aware that non-real zeros exist. They give our graphs these funny shapes, even though there's no x-intercepts or zeros we can find.